What we're going to talk about today is simplifying square roots, and here's our context for why we're doing that. Let's take a look at a problem here, and let's think about some ways we could do this problem. Looks kind of ugly. Would everybody agree that I could, if we think back to the stuff we were doing last week, we were solving quadratic trinomials by factoring, right? We could turn this into a problem like that. If I were to take this expression up here, this 3x minus 4 that's being squared, and I were to FOIL that out, 3x minus 4 times 3x minus 4, do the whole FOIL process, distribute. Would everybody agree I'm going to get an x squared term out of that? I'm going to get an x term, and I'm going to get a number, right? I could combine like terms, and I could subtract the 76, and that sounds like a lot of stuff to do, but I could eventually get to a point where I would have something like this. I would have something in the form ax squared, so I'd have an x squared term plus an x term plus some number equals 0, right? We'd put it in standard form, and maybe, just maybe, we could factor that, okay? Sounds like a lot of work, though, right? Is there an easier way? I mean, we could potentially do it, but is there an easier way? The answer is yes, there is. Let's think back, take a little stroll down memory lane here. Let's go back to the beginning of the year when we were solving linear equations. I told you something at the time which I think probably was very helpful. You might have already known this, but we said that if we could point to a single variable in a linear equation, we could always isolate it with inverse operations, right? We could always work backwards down our order of operations tree, or bottom to top on our order of operations tree, and isolate the variable, okay? Well, how many variables do you see in that equation? How many variables? Just show me fingers there, but how many variables do you see? Yeah, I see one also. There's one right there, isn't there? I can point to a single x. And so the good news is that for quadratics, we can do the same thing. We can just isolate that variable by using inverse operations. So let's think of this in terms of PEMDAS. So we're going to go opposite direction, bottom to top, to isolate. And let's think about how this works. Actually, before I go any further, I want to maybe just add one little thing about, why are we doing this? So the goal is, and we've mentioned this a couple times, by the end of the unit, our goal is to be able to solve quadratic equations. Any quadratic equation I can throw at you, you're going to be able to solve. But we don't want to just be able to solve it. We want to be able to solve it in the most convenient and efficient way, right? So we're developing some different strategies, and we're always going to try to pick the best strategy. Last week, we talked about factoring. Is it always going to work? No, it's not always going to work, right? We ran into a couple instances where it didn't work. We ran into some instances where it was pretty hard. I mean, it worked, but it was pretty hard to do. So if it either eventually, at the end of the unit, if it either doesn't work or it's too hard, we'll move on to a different strategy. What we're looking at today is one strategy that's pretty easy when it works. When we're able to point to a single x in a quadratic equation, the easiest thing to do is just isolate the x. That doesn't always happen, right? Last week we saw quadratic trinomials that had both x squareds and x's, and we didn't have that luxury. We had to do something else. We didn't have a single x. We had x squared and x's together, so this wouldn't work. But in a situation like this, it does, right? So let's think about how we could isolate this x then if we reverse order of operations. One thing I want to point out is that when we're using inverse operations, we don't get to the parentheses step until the end, right? That's the very last step in our inverse operations. Parentheses are grouping symbols. Well, look, we have some parentheses right here. So we're not going to get to do anything inside the parentheses until the very last step. All these other steps really are steps that are outside of the parentheses. So let's just go through the list here. Step number 1, is there any addition or subtraction that we need to undo to get that x by itself that's outside of the parentheses? What do you got to do, Noah? You got to add 5. We got to add 5 because I've got this 5 outside of the parentheses I've got to get rid of. Okay, good. So we cross those out. And we've got the quantity 3x minus 4 squared equals 81. Is there any multiplication or division outside of the parentheses that I need to undo? What do you think? I'm seeing people shaking their heads. You're right. There isn't any. So we can cross that step off, which brings us to the exponent step. Okay, well, there is an exponent. How are we going to undo that exponent? How do we undo a squared? Square root. Yeah, we could square root. Okay. Now, we're actually going to pause this problem for today, and we'll come back to it on Thursday, because that we run into a step here, the square root step, where we need a little practice probably. There's something to taking square roots. I mean, it's a bit of a process simplifying square roots. So we're gonna move sideways and focus for today on simplifying square roots, and then we'll come back and we'll finish the problem and talk about how we can use this technique on Thursday to solve other quadratics. All right, so let's take an example of a big ugly square root. We want to simplify this. Well, when we're simplifying square roots, here's how you can always think about that. We've got a square root of a big number. Our goal is to get, whoops, wrong color. Our goal is to get as much of the number outside of the radical as possible. That's what we call simplifying a square root. So how are we going to do that? Well, there's a trick. Do you remember this from Algebra 1? Do you remember the saying, couples go out, singles stay in? So just show me a show of hands, or just lift a finger here if that's something. I'm curious, how many people have heard that saying? Okay, maybe close to half. All right. So let's review that. Some of you haven't even heard of it. Some of you have, but I bet you could use a little review. We're going to take the number inside the square root. That's called the radicand. Not that we really care about that, but the number inside the square root, and we're going to break that up into factors. We're going to try to break it apart into, we're going to factor that number. Break it apart using a factor tree. We want to write it as a product of a bunch of smaller numbers. So we've got the number 4,410. There's no right or wrong way to use a factor tree. Do you guys remember using factor trees where you start with a number at the top, and every time it branches, you've got to have factors that multiply to the number above? So there's different routes you could take, and we're all going to end up at the same place, but we've just got to find two numbers that multiply to 4,410. An easy way to think about that is, can you think of a number that divides evenly into 4,410? Ideas? No, you got an idea. 10 does. How'd you know? Okay, because it ends in a 0, right? So we know that if we ever have a number that ends in a 0, 10 divides into that evenly. What if it ends in 2 zeros? 100, okay. We could divide 100 into it. So that's one thing we see right away. We could split this up into a 10, and then 10 times 441, right? Okay. What about the 441? Can we break that up into some smaller stuff? There's some tricks for this, but it's hard to find those numbers, isn't it? Can anybody tell me a number that divides evenly into 441 and how you got it? Let me think of one. And you could just try trial and error, but that takes a long time. We could just try a bunch of numbers. Okay, there's some good tricks. I'm going to let you in on some little secrets here. So one really good trick is, if you add the digits up, 4 plus 4 plus 1 is 9. What happens how can you tell if 3 divides into this number by adding the digits? Have you ever heard of this trick? Okay, good. If you take the sum of the digits, if the sum of the digits of some big number is divisible by 3, then the big number is divisible by 3. Okay, that also works for 9, by the way. So 4 plus 4 plus 1 is 9. 9 is divisible by 9, isn't it? So it's guaranteed that 9 goes into that number, all right? So let's figure out how many times. Let's kind of practice this process. We're going back a ways here. This is sort of pre-algebra stuff, but you might be a little rusty on this. How can we divide 9 into 441? Well, we can use kind of a shorthand long division. Does 9 go into 4? No. Does 9 go into 44? Yeah, how many times? 4 times. 9 times 4 is 36. 9 times 5 is 45. That'd be too big. So it goes in 4 times. 9 times 4 is 36. How much with what remainder? How much is left over? 8. 44 minus 36 is 8. So then we're just going to write whatever the remainder is up there, and we'll move on to the next digit. 9 goes into 81. How many times? 9, right? Make sense? Okay. So let's split these apart again. Well, the 10 splits up into a 2 and a 5. I guess we forgot about the 10. The 9 splits up into what? 3 and 3. And the 49 splits up into 7 and 7. Okay, why'd we do that? Here's why. There's a property of square roots that we're going to use here. We know that the square root of a product of numbers, I can split that up into separate square roots. So we'd say in math, the square root of a product is equal to the product of the square roots. See what I'm saying? So we could rewrite this. We've got this 4,410 that we've broken up into all these factors. Well, let's write this 4,410 as a product of all these prime factors. So what I end up with? A 2 times a 5 times a 3 times a 3 times a 7 times a 7, right? So I end up with 4,410 is the square root, or the square root of 4,410 is the square root of my 2 times my 5 times 3 times 3. How would I say that? 3 squared, okay? Times, I've got 7 times 7, so there's a 7 squared. Make sense? So the product of 2 times 5 times 3 squared times 7 squared equals 4,410. Okay? We can use this product up here, and we can split those into separate square roots. So we end up with something like this. I'll color code this. So we get the square root of 2 times the square root of 5 times the square root of 3 squared times the square root of 7 squared. Can anybody see why that was handy? Does something happen here that's convenient? Ah, look at that. The square root of 3 squared, we already said that square roots and squares cancel each other, right? They undo each other. So we've got the squared is canceled by the square root, right? And vice versa. And so we end up then with our final answer looks like I've got this 3 times 7 that no longer has a square root, right? Those are outside of the square root times the square root of 2 times 5. Those got stuck inside radicals. The radicals didn't go away, okay? So this process was handy. Wherever we ended up with factors that were squared, I had 2 3s and 2 7s in my factor tree. Those ended up outside of the radical, right? The factors that were by themselves got stuck inside. We got a little saying that reminds you about that. Couples go out, singles stay in, right? So look at the couples that we had. I'm going to put circles. The way I do this, I put circles around the couples and boxes around the singles. So we had couples of 3 and 7, right? So I had a couple of 3s, gave me a single 3 outside the radical. The couples of 7 gave me a single 7 outside the radical. Singles stay in. Well, look, I had a single 2 that stayed in the radical and a single 5 that stayed in the radical. How about that? Easy. So we can do as big a number as you want to deal with. By making a factor tree, we can take any square root and simplify it pretty easily. Okay? So our final answer then, we could go one step further, couldn't we? we could write this as outside the product of the 3 and the 7, our couples give us a 21, and inside the radical, the product of the singles, 2 times 5, gives me a 10, and that's my answer. Okay? Make sense? Okay? So that's a little bit of a process. Now, this doesn't show up in your printed notes, but it'll be on my PDF notes that are published. Here, I just put together just a little guide for the numbers 2 through 10, some divisibility rules, the tricks for knowing if these numbers divide into a big number. Well, 2, if it's even, 2 divides into it, right? That makes sense. We already talked about the rule for 3. If the sum of the digits is divisible by 3, the whole number is divisible by 3. Same thing for 9, right? We'll skip down here. Same thing for 9. If the sum of the digits is divisible by 9, the whole thing is divisible by 9. We talked about 10. If it ends in a 0, 10 divides into the number. Similar to that, if it ends in a 0 or a 5, 5 divides into the number. So you might be familiar with those. Here's a couple new ones, though. This is kind of a good one. What about 4? Does 4 divide into a big number? Well, 4 divides evenly into 100. So any of the digits in some big number, the hundreds digit or the thousands digit, anything beyond that we don't have to worry about because we know 4 divides into 100. So it's going to divide into every digit beyond the hundreds digit. The only thing we have to worry about is the first 2 digits. So I'll give you an example. Like if we have the number, some huge number, does 4 divide into that? It does. It divides into that because we only have to look at the last 2 digits. Okay? All right, what about 8? 8 is similar to that. 8 doesn't divide evenly into 100, but it divides evenly into 1,000. So we do the same kind of rule, only this time we only have to look at the last 3 digits instead of 2. If 8 divides into the final 3 digits, it divides into the whole thing. Okay? And then there's one really weird one I want to share with you. This one, you may not remember this, but it's just bizarre that this works, but it does. What about the divisibility rule for 7? Okay, there's 3 parts to this, and I'm going to demonstrate with a big number. Let's take, we'll take 868, how about? There's just 3 steps to this. If you take the last digit of the number you're testing, which would be what? 8. So there's my last digit, and I double it. That gives me 16, right? I just subtract that from the number created from all the other digits. So I'd end up with 86 minus 16, right? There's the other digits. 86 minus 16 is 70. If your answer is either 0 or it's a number divisible by 7, then the whole big number is divisible by 7. That's crazy. It's just weird, but it works every time. One other I don't want to spend too much time on this stuff, but it is kind of interesting. I mean, you've dealt with numbers your whole life, but I bet you've never really thought about it this way. What if you have some enormous number? Like, let's say we're talking about cosmological distances, like distances between galaxies, for example, huge distances, really big numbers. If I want to know, for example, if 7 divides into some really big number, well, if this thing's got like 19 digits in the number, I'm still going to end up with some huge number, and how do I know if 7 divides into it? Do it again. Just keep doing it and doing it and doing it until you whittle the number down to something smaller, and eventually you have an answer. Same thing works with 9, for example. I could have some enormous number. If I add the digits of that number up and I get a really big number because there's a lot of digits, I could do it again. Take that number and add those digits up until I get a number that's small enough that I know if 9 divides into it. Okay? All right, but I'm probably spending too much time on that. So we got some tricks. Let's try our new bag of tricks and see if we can simplify this radical. So what are we going to do here? Factor tree. Okay. Lexi, can you tell me, I'm starting with the number 1232. Can you tell me a number that divides into those? I could do 4. Good. Now I could do 2, but 4 is a good idea. 4 is a really good idea. And how come 4 was such a good idea? Let's backtrack for just a second. If we can get perfect square numbers that divide in, then those always break down to pairs, don't they? Right? So we always want to kind of target the perfect squares, which would be 4 and 9. So that was good insight. So we could divide a 4 out of this. 4 goes into 12 3 times. 4 goes into 3 how many times? None, so 0, right? 4 goes into 3 0 times with 3 remaining. 4 goes into 32, 8. There we go. Okay, good. How about another one? What's the number that goes into 308? What do you think? 8 might. It's possible. But we can guarantee you what number does. 2. Is there a slightly bigger one? 4. Because we look at the last 2 digits, and 8 is divisible by 4, isn't it? Okay. Why am I so hung up on 4? What's good about that? Look at that. There's a couple right there, right? There's a couple of 4s. Okay, that's good. So 4 goes into 37 times, right? 4 times 7 is 28 with 2 left over. 4 goes into 28 7 times. Agreed? And then finally, that 77 breaks up into what? 7 and 11. Good. Okay. So we get a couple of 4s. Whoops, wrong color. Very particular about my colors, as you know. Oh, it did it again. This board, you know what? I'm going to save this thing because it's been crashing like frequently, and I don't want to lose all this stuff. I feel like it's about to. Well, maybe not. Couple of 4s, and it looks like I've got a single. Come on. A single 7 and a single 11. So what's that mean then? What's that tell me about my simplified radical? What's going to be outside? 4. I've got a couple of 4s. So I get a 4 outside, and what's stuck inside? 7 times 11. Okay, so did I really have to break up that 77? I mean, if I were, once I get a little practice on this, maybe I could have looked at that 77 and said, okay, I'm not going to get any couples out of that, right? I got a couple of 4s. There's no 4s that go into that. No couples are coming out of that 77. And I could have maybe even just left it as a 77, right? Either way, my final answer is 4 times the square root of 77. Okay, good? Give me thumbs up, thumbs down, thumb sideways here. How are we doing? Okay, how much of this is this review? Or is some of this a little bit new? Kind of half and half? All right. So next issue, fractions. How do we deal with square roots of fractions? Well, there's a couple things we can consider. We'll use PEMDAS. If we're using PEMDAS and we're simplifying, we're going top to bottom. So we're going to first of all consider the parentheses step. Well, parentheses means just grouping symbols. Anything that groups stuff counts as parentheses. Well, look at this. I've got this square root. Oh, this is scary. This doesn't look good to me. Oh, never mind. I guess we're okay. There's all kinds of new features. There's some update, and I don't even know what they are, but all kinds of crazy stuff is happening to me every period. Somehow I get this thing to rotate on a cube sometimes, and I don't know how I did it, but anyway. So look, I've got this square root that's grouping everything inside the square root, right? That counts as a grouping symbol because it contains the 36 divided by 16. So inside the parentheses, first of all, inside the square root, which is gathering all this stuff together, can I simplify that? 36 over 16? What's it going to be? What's the number that divides into both 36 and 16? 4. Okay, good. So I could divide the top and bottom by 4 and get 9/4. Okay, so there's step 1. Okay, now there's another property here. I guess I forgot to include this one on this page. There's another property that we're going to take advantage of. Just like before when we had this property of square roots where I could break a product up into separate square roots, I can do the same thing with a quotient when I'm dividing stuff. So if I've got the square root of a over b, I can rewrite that as the square root of a over the square root of b. So in this case, I can just split the square root into the square root of the top divided by the square root of the bottom, and now it's pretty easy, right? If I take the top and I simplify that radical, if I come down to the exponents, and I want to simplify that, well, what's the square root of 9? 3. Square root of 4 is 2. Done. Okay, that worked out great, but it's not always so easy. Here's a different example. Now this one, it doesn't seem like there's anything we can do, right? 6 is simplified the square root of 7. I can't take anything out of the radical, so it looks done, but it's not. Mathematicians are really particular about this. We can't have irrational numbers in the denominator. We want the denominators to be whole numbers, okay? So we've got to rationalize this denominator. Now, a way to remember that this is something you have to do, here's our rule: no tenths in the basement. You can't have square roots in the bottom of a fraction. So we got to get rid of that. Can anybody remember how to do that? Okay, that you're right. How about more specific? Somebody can tell me, can you tell me a more specific step? Thought I heard something back here. What do I do? I got to get rid of that square root on the bottom. What could I do? What are the things I can do mathematically? You got an idea? Okay. So if I want, my goal here, I'm going to multiply by something, right? And my goal is on the bottom, I don't want a radical. So you're saying I could multiply the bottom by what? Square root of 7. Okay, that's a good idea because the square root of 7 times the square root of 7 is just the square root of 7 squared, isn't it? Right? So that's going to undo, if I think about just that part, the square root of 7 squared undoes the radical, and I just get a 7 on the bottom. That's good. Okay, but we're simplifying. When we simplify, we're just supposed to make the answer look simpler, but it's got to have the same value, right? If I were to type my original problem, ignore all the pink stuff up here, if I typed that into a calculator, I'd get some wacky decimal, right? I've got to get the same decimal when I'm done with this whole thing. It can't change the answer. So if I'm multiplying the bottom by the square root of 7, how can I make sure that I'm not changing the value of my original expression? Multiply the top by the same thing, right? Okay. Now let's think about why that works. Square root of 7 divided by square root of 7 is equal to what? 1. Okay, another stroll down memory lane. If we go back to the start of the year, we talked about some properties of real numbers. What did we say was the only number we could multiply by something and not change its value? 1. That was our identity number for multiplication. What was it for addition? 0. Okay, good. So we're just multiplying by 1, which means we're keeping the identity the same. When I multiply fractions, I multiply straight across. So the square root of 7 times the square root of 7 gives me 7. On the top, I just get 6 times the square root of 7. And that might look more complicated than what I started with, but to a mathematician, that's better because I don't have a radical on the bottom anymore. Okay? All right. So I don't really need all that stuff, do I? No, not for that one. Let's look at one more example. How much time we got? When are we out of here? Oh, that's plenty of time. We can do this. So this is the granddaddy of all square root simplified problems. We got a big, ugly fraction to deal with. So what do we do first? Okay, we see if we can simplify inside the square root. Can I reduce that? Is there a number that divides into both top and the bottom? What number divides into both top and the bottom? And I'll tell you what, if we don't get the biggest number, we can just do it again. What's one obvious number that divides into both? 2. They're both even. And maybe it turns out we can go a step further, but we'll start with 2. If I divide both the top and the bottom by 2, what am I going to get? Whoops. Bottom, I'm just going to get 160, right? What about the top? What's that going to be? Say it again. 189. That's good. Okay, and could I simplify it more than that? It doesn't really look like it to me. Top's odd, bottom's even. 3 doesn't go into the bottom, but it goes into the top. I think that's as far as we can go. And what if it wasn't? We could still do the problem even if it weren't completely simplified inside. It just might be a little more cumbersome. Okay. So now what? We simplified inside the radical. What's our next step? What did we do next? Once we got the fraction whittled down, made it as simple as possible. Okay, good. Yeah, we split the top and the bottom, didn't we? Okay, we're going to use that property. So we'll break it up into separate square roots. And now we just got to work our way down, right? We simplified inside the grouping symbols. Now we've got to deal with the exponents. Well, why is a square root an exponent? I'm not going to bog us down with that conversation right now. We'll do that soon. But radicals count as exponents. Okay, and I'll defend that statement later. I just don't want to take the time right now. So we got to simplify those radicals. Okay, well, we got top and bottom. We got to do them one at a time. So let's start with the top. We got to simplify the square root of 189. So we got to factor 189. Okay, what's a number that divides into 189? 9 does. 9's a good one, isn't it? 9's a good one. So 1 plus 8 plus 9 is 18. 18 is divisible by 9. 9 goes into 18 twice, and it goes into 9 once. So I get 9 times 21. Okay? 9, we know, that breaks up into a couple of 3s. That's convenient. And the 21 breaks up into a 3 and a 7. So on the top then, what goes outside? 3. Okay? What about that 3? Is that part of a couple or a single? Single. These 3s already make one couple, and this is a leftover, right? That 3 is the third wheel. So we got 3 and a 7 are singles. So we took care of the top. We're going to get 3 times the square root of 21. What about the bottom number? We got 160. What's the number that divides into 160? 10 and 16, and that works out great because 16 breaks into a couple of 4s, right? The 10 is going to break into a 2 and 5. Do I even need to bother? No, those are going to be singles, aren't they? Okay, so we could do this. I get my 4 outside, and inside I get a 2 and a 5, which are just going to multiply to a 10. Okay, so we end up then, where are we now? We're down to the step. Let me rewrite this. So this whole thing is equal to 3 times the square root of 21 over 4 times the square root of 10. Looks good. Are we done? What's the one problem with this? No tenths in the basement. Okay, we got to rationalize. We did couples go out, singles stand. We got to rationalize the denominator. So what are we going to multiply the top and the bottom by here? Okay, 4 times the square root of 10. Do we really need to multiply the top and bottom by 4? No, because the only problem, the only red flag at this point is I've got this. Oh, what did I do there? It's like a comedy of errors up here, isn't it? There we go. The only red flag is that square root. So whatever the stranded radical is, whatever the stranded square root is on the bottom, I'm just going to multiply top and bottom by that only. That's the only part I'm worried about. So we multiply top and bottom by the square root of 10. And what are we going to get? 4 times, what's the square root of 10 times the square root of 10? 10. Right? Either you can think of it as the square root of 100, which is 10, or even better, the square root of 10 squared, which cancels the square root. So 4 times 10 is 40. Good. And then on the top, what do we get? So on the top, I get 3 times the square root of 21 times the square root of 10. Okay, the only thing we have to think about here is, are there any couples that we need to pull out? And there aren't. How could we check? I already have a square root of 21 times a square root of 10. Those are like branches of some bigger number, right? Those are like factors of some bigger number. So if I break the 21 down a little bit further, I get a 3 and a 7. The 10 gives me a 2 and a 5. Those are all singles, right? No couples. So everything is going to be stuck inside the radical. What is 21 times 10? 210, right? So I end up with 3 times the square root of 210, all divided by 40. Wow, that's a big, that's a monster square root problem. But we got it.